A few comments before we start today's lecture. So first, remember that your theoretical analysis part of your project is due on Friday. And second, I left some comments on Nectar. If you haven't seen those, definitely look on the course project discussion. So those comments give you a little bit more detailed guidelines than a little bit extending what's on the project PDF description. And finally, today's lecture will be the last one that has webwork homework associated with it for this week. So after today, after this current lecture, you will have all of your webwork for this week assigned. And on Friday, I'll reserve that lecture for the numerical analysis portion of your project, which will not show up on webwork anywhere. It'll be just a component of your project. Okay, now let's begin today's lecture. So this is the kind of thing that we've been studying for the last couple of lectures: second order linear homogeneous differential equations with constant coefficients. So second order meaning you have up to two derivatives here with a non-zero. Constant coefficients meaning these coefficients are constant rather than depending on time. And linear meaning the left-hand side here is a linear operator being applied to x, and homogeneous meaning the right-hand side here is 0. So what I'm going to change now is, instead of homogeneous, let's look at non-homogeneous. What that means is, instead of putting 0 on the right-hand side, we allow a function of t to be on the right-hand side. It doesn't actually have to be a function of t. It could be a constant, then that would still be non-homogeneous. Or it could be an actual function of t. So some examples. So here is an example. If I had 0 over here, then this would be one of our usual second order linear homogeneous blah 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 blah. But if instead of 0 I put something like t squared or t squared plus 7, then that's non-homogeneous. Or if I just put 7, then that's non-homogeneous. And when I talk about the right-hand side, I mean what ends up being the right-hand side after you put things into a certain form. So for example, you certainly could just subtract the t squared over and then look at this and be like, well, the right-hand side is 0, so this is homogeneous, right? No, wrong. This would not be homogeneous because if you write it so that it's a linear operator being applied to x equals something, then that something has to be t squared in this situation, pretty much, or it has to at least depend on t. If you think of the left-hand side here as an operator, something that's operating on function x, that would not be linear. So this would actually be a non-linear thing being applied to x. One way to see that is, one thing that linear things do is if you put in a scaled version of x, then you should get the scalar popping out like that. Right? That's one thing that linear operations should do, in addition to also distributing over sums and stuff. But even this property would fail if you viewed the left-hand side here as L of x. That would totally fail. And you can try that. Try sticking in 2x. Define this to be L of x, then try sticking in 2x, and notice that you get something different than if you just stuck in x and then multiplied by 2 afterwards. So putting this t here screws things up. Okay, so if you want to write this as a linear thing applied to x equals something, then that something has to be non-zero. So even though it looks like the right-hand side is 0 here, this is still non-homogeneous. So the easiest way to see that it's non-homogeneous is to just write it in kind of standard form. Linear thing applied to x, and then shove everything else to the other side. Now, do you have 0 on the other side? No, so this is non-homogeneous. Similarly, sometimes we write things like this. Like if I wrote this, would this be homogeneous or not? It is a linear second-order differential equation with constant coefficients, but is this homogeneous? Yes, even though the right-hand side is not 0, it hasn't been put into standard form yet. So this is definitely homogeneous because when you write it as a linear thing applied to x equals something, that something does end up being 0. Okay, so why are we interested in studying these kinds of things? Well, remember where this differential equation arose sort of naturally? It arose from, well, one place where it arose was a spring mass system, right? Where the spring maybe has a stiffness and a damping coefficient. And what we did is we said Newton's second law, the mass times the acceleration. So here there's an equilibrium position, x equals 0, and there's some direction which is positive x. So if x is the displacement, then x prime prime is the acceleration. And then Newton's second law says mass times acceleration equals the sum of the forces on the thing. And we've got Hooke's law giving us this restoring force, the spring trying to come back to equilibrium. We've also got some damping. This was our crude model for how damping works. So like friction in the spring. And this was our, this is where we got a differential equation of this kind of form, right? Except with a 0 over here. So we just added stuff to the other side. And there is our second order linear homogeneous differential equation with constant coefficients. Now, this is all assuming there are no external forces on the system. The only forces on the system are internal in the sense that they're coming from the spring. Let's call that internal. Anything coming from the spring is internal. So the spring attempting to get itself back to equilibrium, to restore the position back to equilibrium, that restoring force coming from Hooke's law, that's like an internal force to the system. The drag or the friction in the spring, that's an internal force to the system. Now imagine that we introduce an external force. So someone comes in. So there's this like hand coming in. That's my hand. And it just starts, pushing on the spring and moving it around. Not in a way that cares about x, but just some function of time, right? So it just applies different forces at different times. Then how would we incorporate that into our system? Like, say the hand comes in it and it applies a sinusoidal force in time. So maybe sine of t or something. So at time 0, it applies a force of 0. At time 1, it applies a force of sine of 1 radian or whatever. It just applies an oscillating force. Like you go in, stick your hand, and starts pushing and pulling back and forth. How would we incorporate this kind of thing, a time-varying force, external force, into the system? Well, if the force that's being applied is f of t, let's use capital F for force, f of t, then you would just add that on, right? That would just be one of the additional forces that's being applied and contributes to the acceleration of the mass at the end of the spring, right? Then now you have not 0 here, but f of t, right? So you've gone from homogeneous to non-homogeneous. The non-homogeneity, the non-zeroness of the right-hand side, is represented here by an external force being applied to the system. And notice that the time dependence here is explicit. Of course, here there was implicit time dependence all over the place, right? Like, just because x is a function of time, right? So, yeah, the acceleration varies in time because, m times the acceleration equals these things that vary in time because x varies in time. But the acceleration previously, without the external forces, the acceleration only varied in time through how x and x prime varied in time. So the acceleration just depended on x and x prime. If you knew the state, if you knew like where the spring was and how fast it was moving, you would know the acceleration and be able to do perfect predictions from that instant on. But now what we're introducing is something that you wouldn't know just from knowing where the spring is and how fast the spring is going. This is explicit, something that depends explicitly on time, not just on x and therefore on time. Here's another example. This is another physical situation, this RLC circuit, where we ended up with one of our second order linear homogeneous differential equations with constant coefficients, right? And here there was no power source, but that was just something we artificially, we just sort of deleted the power source. It previously was there in what we were imagining. We did that just so it would become homogeneous. But now I want to reintroduce the power source, so there's some voltage here. I don't know what to call it, voltage source. E of t. And then we have seen that you get this differential equation, the E prime of t here. So if you want to remember where this came from, you can look at page 52 in the book. That's where we got this before. But yeah, introducing a power source now makes this a non-homogeneous differential equation. Now I want to describe sort of the way we think about this. So in each case, we think of the left-hand side as kind of a linear operator being applied to x, and then the right-hand side is the output, right? So here, another way of writing this is Lx equals f of t. And if I'm going to write of t in one place, I should write it everywhere just for some consistency. L applied to the function x of t gives me f of t. This is my non-homogeneous linear differential equation. It's basically this. Just where L is this, A, D, this thing. If you just make that be L, then this is a way of writing it. And this is really useful. I encourage you to start using this kind of notation in your Scratch work when you have a linear differential equation, because it will really help you to sort of see things that you otherwise couldn't see if you just write things out in this long, complicated kind of way. Okay, so here's a way of thinking about this. Okay, if you just think about it mathematically, then usually you would probably refer to the x as an input to L and the f as the output. And when you're solving the differential equation, you're interested in figuring out what inputs x to L you could put in order to get the desired output f of t. That's the way we think of it when we think about the function L. But if you think about actual problems like spring mass system, what do you actually control? And yeah, what is usually under your control in an applied kind of engineering problem? What is under your control, and what is the reaction to what you do? Really, the external force, this yellow part, this is the part that's more under your control. So you can come in and push the thing around how you want to. And then x of t, the solution to the differential equation, x of t, is going to tell you how it reacts, how the system responds to what you do to it. Similarly here, what you probably more directly control is the voltage source and how that's changing in time, how the voltage here is changing in time. That's something you can often actually literally just control, what function this E of t here is. And then I, the current through the circuit, or if you had not taken derivatives here, then the charge on the capacitor plates or whatever, that would be the response. That's the way the circuit responds according to the laws that govern the different circuit components. So in each case, the yellow part is the what is being applied to the system, what is under your control, and the I here or the x here that solves the differential equation would be the response. So this is a little bit backwards from how we think about it when we just look at the function L, the input to the system is like the f of t, and if you solve the differential equation, Lx of t equals f of t, then after solving you get an x of t, right? After solving the differential equation you get an x of t that solves it. That's like the response, or the output. So it's the opposite to how L operates. L is like you input x and then f comes out. In practice, it's f that you control, and the x that solves the differential equation is the response of the system. So if you're applying this to like an engineering context, then the way you would think about this is, how can I set up my input? How can I apply an external force here? Or how can I set up this voltage function of time? How can I set it up so that I get the response that I want out of the system? What f of t leads to x of t being what I want it to be? So since it's kind of a backwards version of how we think about how L operates, a big part of the way differential equations become useful is trying to find ways to invert L, basically. So you know how L sends x to f. By applying L to x, you get f. How can I invert it? Given an f, figure out what x's L would produce f from. So if you think about it like L is a matrix and x and f are vectors, which it's very similar to that situation since L is a linear operator. If you think about it like that, it's like a problem of trying to invert a matrix. So trying to solve these differential equations is a lot like trying to invert a matrix, but instead of a matrix, it's this differential operator. Okay, so the analogy between what you're seeing here and the linear systems that you learned about in linear algebra in Math 4a, if that's how you took it, this is a very strong analogy. So we're going to start making a lot more use of that analogy, and we'll discuss that more in the next video.